Okay, welcome back, and we're going to continue to talk about fuzzy logic and some different things. I wasn't very clear on what I was doing last time in terms of finding out the aggregation in two specific cases. So I added something to the slides. They're currently online. This is the second revision I've done to the slides, and they're right near the end. So you might want to, if you're uploading this or downloading it and want to look at it, look at the revision, I think that'd probably be a good idea. And here's the different results you get. If you do minus infinity, you get the minimum. I want to talk about that a little bit. I think that the aggregation -1 is the harmonic mean, which is kind of the way that resistors add when you connect them in parallel. Aggregation is the geometric mean. If you want to compute the interest that you've made in the last 5 years, and you have the interest in every year before that, you would actually do that by a multiplication of the interest for every year. And you would do a 1 plus, but nevertheless, it's a geometric sort of averaging. Then we have our old friend, the average, which everybody likes and everybody uses. And in probability, we know that the average, the law of large numbers says that the average eventually approaches the mean of a distribution. And so that's something which is used quite a bit. We also have the RMS, and we use the RMS usually for the distance between something. Averages can be negative or positive. The RMS is always positive, isn't it? And it tells us how far we are from something. So usually the x sub n is like the error. And if the x sub n is the error, then this is the average error that we have in a mean square sense. And then for aggregation infinity, we have the maximum. Now you've seen this slide before. Let's go to the next slide here. What I did, I wanted to have some fun. I just generated some random numbers between 0 and 1 using a random number generator, and I did it on the right. And the interesting thing, as you can see on the top of the screen, is that the aggregation operation is it's an operation which has a first derivative with respect to alpha that's always greater than or equal to 0. In other words, it's always monotonic as you increase alpha. It can probably stay the same because, for example, if you have, I think this is true, let me think, if all the numbers in your list are exactly the same, all the aggregations are the same, right? So if you have a list and it all says 0 0.5, 0 0.5, 0 0.5, 0 0.5, all of the aggregations will give you a 0.5. But this is a randomly generated list, and I generated the alpha is equal to minus infinity, which gives us the minimum, the harmonic mean, the geometric mean, the average, the MSE, and the maximum. So you can see here that the alpha is increasing from minus infinity, -1, 0, 1, 2, and infinity. And if we look at these different aggregations, we get the results which are shown here on the right. And if you plot those, you see indeed this is an increasing function as a function of alpha. So these are the 6 different points. So don't pay attention to the x-axis. It's minus infinity, -1, 0, 1, 2, infinity. But you can see that it is a strictly increasing function. I tried to take the derivative with respect to alpha of the aggregation operator and show that it was greater than 0. And I just ran into a beehive of problems. It was just a big mess. So I'm still going to try that. I think you can probably take the first derivative with respect to alpha and show that it's greater than 0. But this is certainly an example illustrating that fact. On the right is a totally different set of random numbers. And you can see that again, as alpha increases, that the aggregation increases. So the aggregation always increases from the minimum to the maximum in a monotonic sort of way, strictly monotonic sort of way. So with that, let us revisit the maximum. Now it's hard to show that it goes to the maximum, which I tried to do, not very clearly. But let's take the aggregation using 100. This is not infinity, but it's very big. So I'm going to choose 2 numbers, 0.1, 0.5, and 0.9. And so the aggregation of this, whoops, looks like I left out a right paren here. But, this is something we can talk about. And if it's 100, this should be pretty close to 0.9, right? Because 0.9 is the maximum of the three numbers. Well, let's go through the math. If you look this up and perform the operation on a calculator, you get what is shown in the bottom left here. And you notice this is incredible because on the left side we have 10 to the minus 100th, 10 to the minus 31st, and 10 to the minus 5th. In comparison with 10 to the minus 5th, this and this are zero, right? This is like, what, 26 orders of magnitude smaller than the biggest number here? 26 orders of magnitude. And this one is 95 orders of magnitude smaller than this big number. So this is essentially taking 1/3 0 plus 0 plus uh, the 0.9 raised to the 100th. And then if we take this to the 100th power, we indeed get 0.89. Now, this is not 0.9, but it's very close to 0.9. And as if we continued to do this, then you get closer and closer to 0.9. So I tried this for the aggregation of 1,000, but the calculator wouldn't handle the accuracy. The calculator that I was using, I think it was a spreadsheet, and it just wouldn't be able to take it. So the bottom line is, as expected, for large positive alpha, the geometric mean approaches the maximum of 0.9. And it's similar for the minimum. So you can go and do this for the minimum also, and do it like 10 to the 100th and 8 to the and all of these to the minus 100th, and then take the minus 100th through, and you'll find out that it's very, very close to the minimum. So we can see, at least here for the maximum in this example, that we do get the maximum. So that's kind of cool. And the other thing I wanted to show was the harmonic mean, because I think this is the most interesting aspect of the aggregation operator. That for alpha is equal to 0, you get the geometric mean. That is, you multiply a bunch of numbers together, and then you take the nth root of that. That's the geometric mean. So we see the geometric mean is this. It's a geometric mean. And we perform an aggregation operator. And what we want to do is, first of all, take the log of it, because it turns out that it's easier to analyze if we take the logarithm of both sides. And then we want to take the limit as alpha goes to 0 of this logarithm. So we take that on both sides. And this is well and good, except that on the right side, it's very clear that the denominator, which is alpha, turns out to be 0. The numerator also turns out to be 0, because it turns out to be the log of all of these for alpha is equal to 0 or equal to 1, right? So we're summing up n values of 1. We're summing up n values of 1, dividing by n. So we're taking the logarithm of 1 here on the right-hand side. You see that? All of these, if alpha is equal to 0, go to 1, and we're summing up n of them. So if we divide by n, the thing in the parentheses goes to 1, and we're taking the log of 1, which is 0. So we have a 0 over 0 situation. So we apply L'Hopital's rule. Now, I heard one time that L'Hopital never generated L'Hopital's rule, that he borrowed it, or he bought it from somebody else. In other words, he wanted his name associated with a great theorem. And I checked it out, and it was true. L'Hopital, he purchased this from Johann Bernoulli. You're familiar with the Bernoulli family. They were just a family of geniuses. Like Bach, Johann Sebastian Bach had a bunch of relatives that were very good in music. The Bernoullis were just famous for their stuff in math and science, and you probably know a lot of things named after Bernoulli. The Bernoulli effect, Bernoulli's principle of insufficient reason, uh, Bernoulli random variable, et cetera, et cetera. And they were all different Bernoullis. Well, this was Johann Bernoulli, and he was supported by L'Hopital. And L'Hopital said, you know what? I want to be famous. I want to live forever. So you got to do something that I can put my name on and claim it, and I'm going to be forever. I'm going to be forever famous. And so Bernoulli did that, and he gave him L'Hopital's rule. So it should be called Bernoulli's rule, but money can buy fame apparently, and so we call it L'Hopital's rule even to this day. Now, L'Hopital rule says that what we have to do is we have to take the derivative of the numerator and the derivative of the denominator and apply the limit and see if that happens. So if we take the derivative of the denominator, we just get 1. If we take the derivative of the numerator, which is this log thing, we get the derivative here. And notice I've put x sub n as e to the alpha log x, because that's a better way to differentiate. I don't know what the derivative of x to the alpha is, but I do know what the derivative e to the something is, because that's very easy to differentiate. So I've rewritten it this way. And if we do that, we get that it's the limit as alpha goes to 0 as this. The logarithm comes down from the exponent. And the x of alpha, what happens to that as alpha goes to 0? All of these goes to 1. All of these goes to 1. And so we can actually get rid of this x sub n to the alpha, because we know as alpha goes to 0 that that's going to go to 1. So we're left with 1 over n times the summation of the log. Now, if you remember, this is the log of the aggregation. So therefore, to get the aggregation, we have to raise this to the e power. And so that's what we're going to do next. We're going to raise it to the e power, the exponential of this thing. Now, if you sum things in the exponent, you guys remember this, of course. This is elementary algebra, I believe. If you sum up things in the numerator, that's the same thing as multiplying them in the other way. So this is the pi, this is the product notation. I assume you haven't seen it, or you probably have seen it, but the pi notation says we don't add a bunch of numbers. Sigma says we add a bunch of numbers together. The pi notation says that we multiply a bunch of things together. And so we get the product of n is equal to 1 to n of x sub n raised to the 1 over nth power, which is exactly the 0th mean, which is, I think, just fascinating. A bit. Fuzzy is very interesting. But you will notice that for fuzzy logic, the expert has to fill in the table, right? If this, then this, then so you have to fill in a table. So if you have 3 antecedents here and 3 antecedents here, it turns out you have to make up 9 rules, right? So therefore, it's kind of limited to cases where you have a limited number of forcing functions, a limited number of antecedents associated with it. Imagine, on the other hand, if you had 3. Well, if you had 3, you'd have antecedent, antecedent, and then kind of in the z direction, you'd have an antecedent also. And you would require, if you had 3, you'd require 27 rules. So you can see that this grows exponentially. And that ain't good. It isn't good to grow exponentially. If you had 4, well, that's 2 to the fourth. So or 3 to the fourth, what is that? 81. You'd have to fill in 81 rules in that 4-dimensional matrix, and that just becomes too much. So do you see that? The problems that we've looked at are 2 dimensions. We have 2 antecedents, and we fill out the table for the 2 antecedents. For 3 antecedents, we would have a 3-dimensional cube, a 3 by 3 by 3. And many times you want more than 3. You want 4 or 5, and you want 4 or 5 membership functions. So it depends on your tessellation. If you tessellate it too fine, you're going to get even more. So this exponentiation is just kind of crazy. And it's something that prohibited AI from doing stuff for a long time. I was fortunate at the University of Washington, to work with a guy named Bill Combs. Bill Combs was a Boeing engineer, very fascinating guy, a very, very solid Christian. He actually had a doctorate degree, a doctor of divinity, but he was an engineer because I guess pastors don't pay as much or something like that. But he was an engineer, and he was an original thinker. He thought of a lot of stuff that was really cool. And so he came up with something which became known as Combs control. And it's a type of disjunctive. What do I mean by disjunctive? I'll prove that. I'll show that in a second, as opposed to conjunctive. The Mamdani rules are conjunctive. The um, the Combs rules are disjunctive. So we call it disjunctive versus conjunctive configuration of the fuzzy logic thing. So let me show you. Okay, here in the upper right, I hope you can see, and I hope that the little box doesn't cover him up. You can see Bill Combs, and we we worked together. And I did not believe his work initially until I went through the mathematics of it. And here's what Bill Combs suggested. Conjunctive logic, such as Mamdani rules, talk about tightly linked reasoning. So if you want to turn your car right, and you have a lot of controls, you can turn the left tires slightly right, or turn the front tires slightly right. You can turn the turn the rear tires slightly left. You can lightly brake the right tires, or you can slightly accelerate the left tires. Those are all different ways which you can turn right. Do you visualize that? So that's all the ways that we can turn things right. So if we had these as the input to our system, we would have to come up with rules that say if how much we turn our tires slightly right, and we turn the rear tires slightly left, and how much we lightly brake the right tires and slightly accelerate the left tires. So you can see here, in order to use conjunctive Mamdani sort of control, we actually have to weight these four, and see what happens. And the interesting thing that Combs noticed is that there's many cases where there's redundancy. We can turn the car right by using any one of these singularly. So this is the union of let's see, is this right? I'm not sure that that's right. I'll check it and correct it. So this is the idea of Mamdani control. Now, Mamdani control uses L antecedents, and here we have four antecedents. It uses n fuzzy partitions. In other words, for each antecedent, we have to have fuzzy membership functions, right? Those little triangles. And we're going to have n of those. So it turns out we have n to the L rules. This is the scaling that I talked about previously. We would have to take a square, and we would have to make it into a cube, and then a four-dimensional cube, whatever that is. And so the rules grow exponentially, as we can see. So n is the number of fuzzy partitions. That's the number of fuzzy membership functions we have. L is the number of antecedents, and I'm assuming that the number of antecedents is the same for all of the fuzzy partitions. And yeah, the number of fuzzy partitions is the same for all of the antecedents, all of the inputs. And so we're going to have n to the L rules. That's a lot of rules, and we would like to avoid that. So Bill noticed something called disjunctive, loosely linked reasoning, where some of our controls are redundant in some sense. I'm giving you an example where they're redundant in an obvious sense. For example, if A1, if we turn the front tire slightly, then we turn the car right. That's what C is. We turn the car to the right. Or if we turn the rear tires slightly left, then we turn the car to the right. Or if we lightly brake the right tires, then we turn the car to the right. Or if we slightly accelerate the left tires, then we turn the car to the right. So you see the redundancy here in the fact that up here, everything is linked by an and. Down here is linked by an or. And this turns out to be very, very consequential. And one of the reasons is that the number of rules, if you have L antecedents and N fuzzy partitions, then it turns out, and we'll illustrate this, that there are L times N rules. In other words, there's no exponential growth. Now, these antecedents must be related. In other words, you can do the same thing with many inputs, but nevertheless, it's very interesting. So this leads us to what I want you to prove for next week. This is the law of importation. It says that the intersection of AK implying C is exactly the same as the union of AK implying C. Over here, we have the conjunctive thing. This is the Mamdani control over here on the left. On the right, this is the Combs control. And they're actually equal to each other in the case of Boolean logic. And I want you to show this in the case of Boolean logic, that with Boolean logic, that these two operations are equivalent to each other. Now, it turns out they're not equivalent to each other in fuzzy logic. We've seen a lot of places where fuzzy logic breaks down and doesn't have some of the beautiful aspects of Boolean logic. And this is one of the cases where it does, where that doesn't happen. So again, this is exactly true for Boolean logic, but it is not true for fuzzy logic. Whether you use the min-max or whether you use the sum product, doesn't matter what you use. It's not going to not going to work. So this is cool. So here's what we have now, and here's some of the properties. Scalability. With the conjunctive reason, we see that it's exponential. For the disjunctive reason, it's linear. So with the disjunctive reasoning, we can add more and more antecedents and still be okay. The plasticity. Now, what is plasticity? That means what happens if you lose something. Let's go back to the Mamdani control. If you have a bunch of things that are linked by an and you lose one of these breaks, you lose one of these. Say that you're no longer able to lightly brake your right tires. Mamdani control says that we have to combine all of these in order to turn right. Well, what happens if A3 breaks out and we lose that sensor? We can't do this anymore. So we only have A1, A2, and A3. Well, all of a sudden, our fuzzy control becomes not very useful in the sense that we don't have all of the data that we need to turn the car right because we have lost one of the sensors. And that's because we have the ands here. And so the conjunctive tightly reasoned Combs control is much better than this. Mamdani is very brittle because if we lose one of the sensors, we're not sure exactly what to do. Let's contrast this with the Mamdani control. Notice that if A1 or A2 or A3 or, you notice because of the or, we can lose one of these and we still have something to fall back on. If we lose that we can turn the car right by lightly braking the right tires, we still have these three other ways to turn the car to the right. And these three things that are left are still able to accomplish this. So it's for that reason that we call the Mamdani control brittle and the or rigid, if you will, the conjunctive control. This is Mamdani. The disjunctive, which is the Combs control, is more plastic. Another thing is coupling. In Mamdani control, every antecedent is connected to every other antecedent. In disjunctive reasoning, it isn't. Robustness for conjunctive, I guess this goes back to the idea of the idea that if that we can be plastic or rigid. The fault tolerance is low for conjunctive reasoning. Why is the fault tolerance low? Because if we lose a sensor, we're out of luck. We don't know what to do with it. We'd have to go back and you'd have to put some mechanism in to fix it if we lost a sensor. However, for disjunctive reasoning or Combs control, we have a high degree of fault tolerance. We could actually go back to the original thing with the ors, and we could actually lose three of these. So we have degradation, but it's certainly graceful degradation. Whereas for the conjunctive or the Mamdani control, we have immediate failure if we lose one of the antecedents of one of the sensors. For cognitive parallel, this is something which was claimed by Bill, and this is the way he thinks outside of the box. For low order systems, CR most closely parallels human interference. CR is conjunctive reasoning. Why is that? Because I can think about things such as I want to invest in the stock market. Well, let's see, the interest rate is going up and the S&P has fallen, and I can look at all the combinations of those in two dimensions, right? If I get more than three or four antecedents, I can't think of all of that. If the S&P goes up, if the interest rates go down, if the Dow goes down, if the tech sector goes up, I can't think of those. I only have to think about them one at a time, and I try to concatenate them in some sense. So, according to Bill, for complex systems, disjunctive reasoning most closely parallels human cognitive inference. Another thing is the actual parallel and distributed processing ability with Mamdani control. Everything is connected to everything else. All of the rules are connected by a rule in that matrix, and therefore you cannot use parallel processing. Whereas disjunctive reasoning is very good for distributed processing because you could have each one of the processes evaluated separately and then concatenate them in the end. So these are some of the interesting things about that. One of the things that we discovered working for conjunctive or disjunctive reasoning, Holmes control, is that basically that it corresponds to an actuator. And this is kind of interesting. You don't have to go through all of the defuzzification. Well, you do, but you use it to get what's called an actuator function. What's an actuator function? An actuator function is shown here on the bottom. You get a signal from a source, you go up to this function, and then you figure out what the consequent is just by looking at a one-dimensional function. Now, why is that? Let me see if I can illustrate this. It's a little bit tricky, but we can do this. On the top, we have n implies L. So this n over here implies the L over here. Okay. So therefore, the more negative this is, the larger I want this. Z implies the medium. So the middle implies the middle. And the large, the P implies the small. So P implies the small. So you see it's backwards. It's N implies large, Z implies middle, and P implies small. I guess you can think of this as negative, near zero, and positive. And this is small, medium, and large. So that's what we have. Excuse me. Okay, so this is what we have now. How do we unpack this? Suppose that our sensors read the following. Suppose it reads 2/3, 1/3, and 0. So one of the sensors reads 2/3, another one reads 1/3, the other one reads 0. So here we have it. One of the sensors reads 2/3, which is here. This is the fuzzy membership for one of the functions. The other one reads 1/3. So the result is actually -2. So for -2, whatever this is measuring, that the 0 has a fuzzy membership function of what? Of 1/3, and the n as a fuzzy membership function of 2/3. So we take these. Whoops, what happened? So we take these, and this again is the antecedent. We use it to measure the consequent. And so we take this red value here, and we use it to scale the m value here. Remember, the negative goes to the large, so the negative value of 2/3 is used to weight the large value. Then we can do the regular defuzzification. We do the regular defuzzification by adding up this red curve with the dashed black curve and then taking the center of mass. I like the center of mass because this is exactly where it balances. If you were to take, if you've taken statics, for example, you know that if you have a beam, which is a weird sort of shape, you can compute the first moment of the beam, and that's where it balances. If you want to balance the beam, that's where you put your finger, and one side would balance out the other one, and you could actually balance the piece of wood or whatever on your fingertip. So this is the center of mass. And the center of mass is the defuzzification that we choose to use. Now, for the for the result of -2, then, which is -2, we have a center of mass of 5/3, turns out. Okay. So this finger here is pointing to about 5/3. Now, what's interesting is we can repeat this for every single value. We can forget the input. Let's put the center of mass all the way to the left, and we begin to slide it across, and we get a number. Like here, we got 5/3. Here, we would probably get I don't know what we would get. We would get 0 probably. And then as we slid it across, we would get different values. So as we slid this number across, we would get different values. We would get the black and we'd get the red. And you can see that the black and the red start to pinch together. And then they begin to spread out. And then this positive thing is introduced. Well, it turns out then that for every S sub k, every sensor measurement, we get a single number out for every single measurement. For every measurement, we get a single number out. So if Sk is equal to -2, it's 5/3. If we move it up to 0, it's going to be, well, it's going to be a 1, right? If we move it up to 2, it's going to be something else. So as we move this up, every time we have a number associated with whatever value is on there. So we can take that number and we can actually make what we call an actuator function. And we see, for example, for -2, which is about right here, we said that it was what? That it was 5/3. So it's about right here, right? So for -2, it was 5/3, which is right. And if we took this point and we moved it back a little bit, it would get bigger. If we moved it forward a little bit, it would get smaller, all the way down to the 4, which is the value way over here. What would be the center of mass of that? So the interesting thing is that for Mondami control, if we look at just the effect of a single sensor and its consequent, use that disjunctive control, then we don't even have to use the fuzzy functions. We basically use this actuator function instead, and we can derive that from our fuzzy function. We can derive this from our intuition. So you can think of this system as being generated by your intuition. And if this is generated by your intuition, this maps to an actuator function, which is something which you can substitute in order to figure out what is happening. So that is fascinating, I think. Okay, so that's Mamdani control. We're going to explore now a totally new topic, swarm intelligence. Now, if we were live, I would ask each one of you to look around and find 2 different people and just identify 2 different people. And then what I want you to do is I want you to pretend that those 2 people are fighting and you want to be their protector. You want to move in the middle of them. And the question is, what happens? What happens? And that's the first example that we're going to explore. Let me tell you a little bit more about swarm intelligence. Swarm intelligence is dumb bugs doing smart things. I mean, you think of the ant. How does the ant figure out how to get from the Milky Way bar back to its nest? And there's a big line of ants. The way it does is it lays down a little path of pheromones. So once an ant finds it, man, we have ant problems in our house. Holy Toledo! I got bug spray all over the place. And Friday we're having a guy come in and spray for ants, but we have ants all over the place. And I see these little lines of ants going back and forth from the Milky Way bar to their nest, and I thought, wow, that is really really cool. Um, so how does that work? It works because an ant, once it finds food, it goes back to its nest and lays a little path of pheromone. And that pheromone evaporates slowly. But then another ant will come, they'll sniff the pheromone, they'll go to the Milky Way bar, they'll follow the pheromone to the Milky Way bar, then they'll go back to the nest and they'll lay down some pheromone. And and so the next ant that comes even has a stronger sense of this pheromone. So it follows the pheromone to the Milky Way bar, and then it goes back to the nest. And pretty soon, this pheromone trail is just packed with ants going back and forth. It's really incredible. And that's the reason that that happens. What's even more interesting, suppose that you had a bridge, you had some water here, you had some water, and you had one bridge that went across and another bridge that went across, and your Milky Way bar was up here. And it turns out that this bridge from the nest is a shorter path than if you went to this bridge, which was further away. Now, either one of those could be a path. Guess which one the ants choose eventually? They choose the one with the shortest path. Why is that? Because the one with the longest path, the pheromone evaporates more quickly, and therefore the ants don't follow it anymore. Isn't that interesting? When I first came to Baylor, there's ants all around Baylor. Have you seen them, the little piles of dirt? And I like kicking them over and watching them swarm around. And I try to figure out the rules that they're following. Like for the ant, the rules are very, very simple. They just go with the pheromone and they choose the strongest pheromone and begin to follow it back and forth. Um, so I kicked over an ant, and I kind of bent over. I grabbed the top of my knees, my pants on the top of my knees, and kind of bent over. And I was looking at them and going, oh my gosh, I'm trying to figure out what happened because it turns out these ants are coming out and they don't go real far from where their nest is. They go a certain distance and then they kind of come back. We can talk about that later. But I was trying to figure out the rules just by looking at them. So I was standing there bending over, grabbing the right above my knees, my pants. And this woman came up and she said, "Are you okay?" Because it looked like I was actually bending over and ready to drop or to vomit or something, but said, "Yeah, I'm okay. I'm just watching the ants." So ants are very, very cool. Now it turns out that these dumb bugs doing smart things are something that we can learn from. One of the things is application of a parameter to the bugs. Another one is learning from different swarm bugs. There's something called the leafcutter ant. Now, what the leafcutter ant does is it forms the conga line and it gets little pieces of leaves and it wants to get these leaves back to the nest. You got it? So what does it do? It picks up a leaf and then it starts back to the nest. And as soon as it meets another ant coming the other way, they exchange the leaf. And so the new ant goes and it goes towards the nest until it meets another ant coming back and they exchange the leaf. And then it goes onward, and that's the way that the leafcutter ant gets the little leaves back to the nest. Now, what can we learn from that? It turns out that Amazon actually used this for a while because it turns out initially that they had specialists. This was before robotics. They had specialists gathering things, and some of them were kind of slower than other ones. Now, notice the algorithm, which is kind of cool. Suppose you have a really lazy ant. Okay. If you have a lazy ant, that ant is going to come back real slow and it's going to take your leaf and it's going to go really slow this way. And if all the other ants are quick, you don't worry about that slow ant, right? It's robust in the sense of filtering out the operation of that real slow ant. So at Amazon, they used to have people which covered specialty areas. There were people that kind of covered books. There were people that covered kitchen appliances, et cetera, et cetera. And what they would do is they would put out the order to these people, and everybody would gather what they were supposed to do and put it all together and do the shipping. Again, this was before everything was roboticized. But the problem is suppose that you had one lazy person there, one lazy person that was in charge of, I don't know, candy. And he just took all day to get the candy. He would be the one that slowed down the order quite a bit, right? So Amazon abandoned this and went to the leafcutter ant. They would have people go from place to place and they would have orders and the person would go to it would fulfill the order, then it would go until it met somebody else whose task was done, and they would say, here's the order, continue to fill the order. And that person would take the order and begin to fill it some more until they met the next person in line, which says, I'm all done. And then they would pass on that task to them. And you see what would happen if you had a very low performing person that you couldn't fire for some reason, like a tenured professor, right? Then, uh, then what would what would happen? You would be robust to the slow worker, right? So the early Amazon learned from the leafcutter ant. Another example that we published was the use of swarm intelligence, kind of ant intelligence for communications. You want to have communications over unused channels, especially if your channels were had some sort of maximum bandwidth or slowed down because of overuse. So one could actually use a pheromone, the equivalent of a digital pheromone, in order to choose the best path to get from, say, your computer to a central server somewhere. And so that has been applied. And there's been a number of other places. So we can learn from bugs doing interesting things. So let me get back to the example that I was giving you before. If we were live, I would ask you to pick out two other people. I would ask you to be their protector. And so your job is to move between the two other people. Does that make sense? So there's two people you've chosen at random, and your job is to move to protect yourself or to protect them from each other. You're the peacemaker. Blessed are the peacemakers, right? These guys want to fight, and you become the peacemaker, which goes in the middle and kind of mediates the conflict, if you will. Now, the interesting thing is throughout the swarm, everybody chooses two different people. So as you're trying to move yourself to be in the middle of the swarm, one of the people that you've shown is also trying to move themselves to move between the people that they have chosen. You get the idea? Now you notice that just like the ants, the rules are the rules are what? The rules are very, very simple. And that's the thing with bugs. The rules are very, very simple, but they have an interesting emergent behavior. Like with the leafcutter ant, very simple rules. Like with the ant getting from the Milky Way bar back to their nest, it's a very, very simple rule. Follow the pheromone. With the leafcutter ant, it's to carry the leaf until you meet somebody coming back the other way, and then give it to them, and they will take it and they will turn around and they will go the other way. So this is a third example. What happens if you were the peace protector? Can anybody offer me a what might happen if indeed that was the case? What would happen to the group of people? All of you guys choose two different people and you all try to be a protector. I want to see if you can think. It's not easy. That's the interesting thing. That simple rule is still not really easy. Okay, let's see. Where'd you go? Where'd you go? I'm trying to get to the. Oh,
Dr.
don't.
Marks,
Yeah, what I do?
would we all get in a circle?
Ah, okay. So that's one thing. We'd all get in a circle. We'd all get in a circle. Anybody else have a guess? Ah, come on. Well, this is what you get for logging out of Google Sheets. You got to go back to your phone and enter a stupid. Okay. I wish there weren't bad people in the world, but there are. Makes you do all of this other stuff. Anybody else have a guess? Okay, get in a circle.
Would we
Nobody
all get closer and closer together?
would all get closer and closer together. That's a second guess or a second analysis. So it began to group together or get in a circle. Anybody else?
Is the assumption that once we get like as close as we can, we stop moving, or is it a constant motion?
Well, you always move yourself to be in the arithmetic mean, in other words, the middle of the two people.
Okay.
See, this is the beauty about swarm intelligence. And by the way, this is designed. You just don't come up with simple rules and figure out an emergent behavior. So let's take a look at this and let me show you what happens. You see my screen, right? Oh, okay. So you saw that, yep, they all gathered in one place. Interesting, but I don't think obvious. So who was it that said they clumped together in one place?
believe that was James.
That was
That
James.
was me.
Hey, James, good job, man. Good job. How did you figure that out? What went through your mind to figure that out? Because I'd like to hear your thinking process because it was clearly correct.
What really was no thinking process. I just watched the videos before lecture.
Okay. Okay. Well, thank you for your honesty. Okay. That's one way to get that. Okay. So if you stay up with the sheet, you can do great and wonderful things. Um,
In in the instance of this video, they seem to be they packed into one location, but I wasn't sure if area was involved. In if they had like a finite area, would they try to maximally pack themselves?
yeah, they just tried to. Now, the difference is suppose you have one set of bugs and you have another set of bugs, and nobody in this set is trying to protect anybody in this set. So they're totally separated from themselves. In that case, you would have the collapse into 2 points. Okay. In other words, if they were totally disconnected from each other, they would collapse into 2 points. Okay. Does that answer your question, Riley?
I was more so imposing like if there is a minimum distance that they could be as close to each other. So if they can't collapse into a single point because say bug one has a minimum area that they can exist, would they maximally pack say like in like a hexagon?
Okay. No, they don't. They no hexagons here. It's just a big clump. I have seen no geometric formation here. It's all just in a clump. Okay, wasn't that interesting? Let's do another one. This one's called the coward. You have the same swarm, and James is not allowed to answer because because he's watched the video. So don't answer if you watch the video. So you have two two different bugs that you identify, just like before. You choose two bugs at random. But one of them you're afraid of, the other one is your protector. So you have a bug that you're afraid of, you have a bug that's a protector. And what you want to do is you're a coward. This is called the coward swarm. So what you want to do is you want to move yourself to put the protector between you and the bully. Get the idea? Two bugs. One is a bully, one is a protector. You want to move so that you put the protector between you and the bully. So if you haven't watched the videos, what do you think happens here? Anybody? If nobody answers, I'll ask James.
Will everyone just kind of move away from each other, just disperse?
Okay, why do you say that?
Because I'm thinking each bug individual is trying to get away from at least one other bug. So I feel like if you just kind of repeat that en masse, all the bugs will just go away from each other.
Okay. Okay, so we have that there's a dispersal, which is exactly the opposite of the peacemaker, right? The peacemaker, they all
Yeah.
clump together. With the coward, they all disperse according to you. Anybody else have a guess? Okay, James, spoiler alert, what happens?
They all run away from each other.
They do. So let's take a look at that. Hey, you guys were right. They dispersed, didn't they? Again, for all of you like me, when I saw it the first time, I wasn't sure what would happen. It's kind of like when you look at it for a while, you say, "Of course, this is what happens." But I think when initially presented with it, it isn't obvious at all. Okay.
Dr. Marks.
Yes.
So in that example, like when the bugs decide who they want to act as their protector and who they're running from, is that something they decide at the start and then stick with the whole time, or is it something they're
Yes.
constantly looking at?
No, they decide
Okay.
it in the beginning. So in this software, a random number generator was used to pick the protector and the bully. And so that was done in the beginning, and that's the way it stuck. So, yep.
So can you explain, because in the simulation at the very end there were multiple of the bugs that were floating across the screen pretty fast. So like at what point do they change direction for any reason? Like,
That's a good question. I only know what I showed you.
okay.
I and that's an interesting point because in the beginning they're all going like this, And what you're saying is at the end, they started to go like this. And that's weird. No, you're exactly right. And I don't know why. I don't know why. But again, isn't that interesting? From such simple rules come this very strange emergent behavior. And even now, with those simple rules, as Gabriel pointed out, we don't even know what happens to these bugs that have them turn around and go the other way. I mean, that's just fascinating. I don't know why. I'm gonna have to think about that. But again, you can see with very simple rules, you can have a collective that does amazing stuff. Um, so we have swarm control too. You know who the big swarm control is? It's in the news lately. It's a guy that controls the swarm of the economy. And in many places, groups of people are modeled as swarms. One of the places I've seen it, for example, is crowd control. Like if you have a panic in a theater or something, how these people will evacuate and they do a swarm sort of thing. There was a movie called Finding Nemo. And if you look at the credits at the end, there's somebody that is in charge of fish swarming. So they had these beautiful schools of fish kind of swimming around in a beautiful pattern. And so there was one guy that was in charge of that. I'd be interested in finding out what the algorithm for that was since it was so beautiful. Uh, yeah, we have lots of interesting results, but the one big knob that we have is these people controlling interest rates. You know, everybody, this guy at the Federal Reserve, they turn up the interest rates, they turn down the interest rates, and this impact upon the swarm of economics is amazing. And it's kind of known in the sense that we do have the history of what happens when interest rates go up and down. But it seems to me that's a fascinating control that we have over the swarm, if you will, of investors. And anytime you have a lot of independent agents doing smart things or doing simple things, you can you can control them in this way. So we also see applications there. Now there are cases where you have these drones going up, and these drones are usually have a formation, if you will. That isn't that isn't the sort of swarm intelligence that we're talking about, because they're not following simple rules. They're instructed on how far to stay from other drones, and because of that instruction, they form these interesting patterns. And it really isn't dumb drones doing smart things. It's more that smart drones doing smart things. Each one has their individual rule. Um, let's see if I can think of some other things. Oh, this is interesting. When an ant hill is attacked, when an ant hill is attacked, it turns out that some of the worker ants begin to turn into army ants. They are recruited, if you will. It's like they put a draft on, and the worker ants become army ants. But they do it gradually, and not all of the worker ants become army ants at the same time. And one model I saw said that every worker ant has a threshold of danger, and everybody has a different threshold of danger. Some are low, some are high, and as danger increases, if that threshold is exceeded, they turn into an army ant. And so those worker ants with really low thresholds actually become army ants very quickly, whereas those with higher thresholds remain worker ants until the end. So even here we have a very interesting simple rule that models the way that ants, dumb bugs, do interesting things, like turning army ants gradually into army ants or fighter ants. I'm not sure what they're called. So, okay, let's see. What time is it? Okay, 1:37. I don't think I have time for the next thing. Any final thoughts at all? We'll come back with some more examples. And if you're interested, and I appreciate people that are energetic and like to go to the website and look at things like James did, to see what other things we're going to talk about. We're going to talk about termites. So here's the question, and see if you can answer it before you look at the video, which is posted on the site. We have termites going around, and there's pieces of wood scattered all over the place. or I like to think about it, you drop a bunch of Skittles on the kitchen floor, and you put together you release these little robots, and the robots come out and they move randomly around. And if they bump into a Skittle, they pick it up, and they keep on moving randomly around until they find another Skittle. And if they bump into another Skittle, they put the Skittle they're carrying down. And then they roam around and they bump into another Skittle, they pick it up. They run around until they bump into another Skittle, they put it down. And this process is repeated. And this is an algorithm which has been proposed for the way that termites clear, if you will, pieces of wood that kind of muddy things up. And I've also heard it referred to as a way that ants care for their dead, a certain species of ants. They run around until they find a dead ant, and then they run around until they bump into another dead ant and they put it down. And so the question is, what's the emergent behavior here? What happens here? Again, something which isn't very clear, but nevertheless is interesting. So we'll look at that next time. Then we'll look at some predator-prey swarms. And one of the things I'm going to ask you to do eventually, I want you to write your own swarm software. I want you to come up with something that we haven't done here, or a big variation on what we've done here, and actually write something that illustrates swarm intelligence from your perspective. What dumb thing can you have a bug doing that shows a emergent behavior? And there's lots of different examples. So that's coming up, and that's a warning. I don't care how you do it. You can do it in MATLAB or Python or whatever you want to do it. But then we're going to you're going to turn it in. You'll turn it in eventually to Box with some sort of documentation. But then I'll ask for volunteers that come up with things that are interesting. Unfortunately, we can't do the whole class, but I'll ask for people that come up with interesting things, and you can show us the rules that you used and the emergent behavior that you saw. And I find this is one of the most fascinating parts of the class in terms of swarm intelligence and what people can get. Okay? Okay, guys. Thank you much. Take care. Be of good cheer.